Hello everyone, and thank you for joining us for the latest Surface Measurement Systems webinar. Today I'm very happy to welcome Dr. Susanna Melisso, a new addition to our team, our scientific team, who will be exploring the topic crosslink density effects on the hysteretic behavior of keratin fibres in water sorption isotherms. Now, before we get into the presentation, I'd like to remind everyone that we have a live Q&A at the end of today's session. So if you would like to engage and address any queries to Dr. Melisso on this topic or any other DVS related subjects, you can do so in two ways. You can submit a question in writing in the questions tab, which you'll be able to see in the control panel to the right of your screen, or you can raise your hand at the end of the session and I will let you know when you can unmute your microphone and ask the question yourself over the microphone. So that's, once again, you can submit your questions in writing using the questions panel, or you can raise your hand if you would like to ask your question over your microphone. So as I mentioned, today we're very lucky to have with us Dr. Susanna Melisso of Surface Measurement Systems, the newest addition to our scientific team. Susanna first completed her master's in chemistry and medicinal chemistry at Imperial College London, working under the supervision of Dr. James Wilton-Eli on multimetallic MRI contrast agents. She then joined the Institute of Chemical Biology in 2017 and completed her master's in chemical biology, focusing on small molecule interactions with human hair, before beginning her PhD in 2018. Under the supervisions of Professor Darrell Williams, Robert Law, and Oscar Sess, Susanna's PhD continued her master's work in collaboration with Procter & Gamble. The focus of this work was measuring interactions of small molecules with hair keratin using multiple techniques, including dynamic vapour sorption, solid-state NMR, and high-performance liquid chromatography. Susanna completed her PhD in 2022 and joined Surface Measurement Systems as part of the application science team. So, as I'm sure you'll agree, she is an expert to speak on this topic. So, without further ado, I will hand over to Susanna to begin her presentation.
Hi everyone, thank you John for that introduction. Today I'm going to be talking about some of my research I've done with hair and this project I did during my PhD. So we'll be looking at how the crosslink density of hair fibres affect their water sorption properties. So just to give an overview of the talk today, I'll be giving you an introduction into hair structure and why we're interested in hair water sorption. I'll be going through the methodology of our analysis. We'll talk about some NMR, going through some NMR characterization of hair fibres. And then finally, we'll go through the DVS experiments, analysing the hysteresis, and hopefully coming to a conclusion. So, why are we interested in water sorption properties of hair? Well, the hair care sector is predicted to reach a net worth of over $112 billion by 2026, with a large component of these sales coming from hair dyes and hair colorants. And so clearly there's a huge market when it comes to developing and formulating new hair care products. But understanding the properties of hair is key for successful formulations. And even with about 50 years of research, there are still some fundamental properties that we don't yet understand. Another component, another key concern when it comes to formulating hair care products and dealing with hair altogether is hair damage. So we've got some nice confocal images here of untreated hair, or which is sometimes called virgin hair in the hair care industry. And we can see here we've got some nice flush cuticle scales on our cuticle. Whereas if we look to the dyed hair, we can see that that cuticle has broken up a little bit. Those scales are quite smaller. And we've also got some dark regions, which indicates cuticle loss. So clearly damage has a real big effect on hair structure, and this has an impact on those fundamental processes. Water management in particular can be quite negatively affected by damage. And so it's really important to understand the physical processes behind the water sorption properties of hair. So here is a very brief overview of the hair structure. We've got that outer cuticle, which you can see in this really nice SEM image. Inside the cuticle is a cortex, which is filled with the cortical cells. And then we have the medulla, which I won't be talking about too much, as it's not present in most hair types and is mainly a porous region of the hair fibre. So to go into a little bit more detail, hair is primarily made up of alpha keratin. Keratin can come in the form of both alpha keratin and beta sheet keratin, with the beta sheet normally arising from damage and disorder. But the hair, a healthy hair fibre, will be mainly made from alpha keratin. Alpha keratin aggregates to form intermediate filaments, and then these aggregate together to form higher order structures. To begin with, they aggregate to form microfibrils, which then bundle together to form macrofibrils. Now, macrofibrils are what constitute the cortical cells. You have macrofibrils embedded in a matrix, making up the para, ortho, and filocuticle cells. The cortical cells themselves are embedded in a cell membrane complex, which make up the cortex. So, as you can see, it's quite a complex structure. It's very hierarchical, and this is what presents one of the challenges when it comes to analysing hair, are all the different regions and all the different levels of order. But sometimes it is helpful, especially in making models to do with hair, to consider hair as an amorphous biopolymer with crystalline regions. The crystalline regions being those intermediate filaments. So here is a water sorption isotherm for untreated hair, and we can learn a lot just from this sorption isotherm. It has a type 4 character with a characteristic hysteresis. It's well understood that at low relative humidities, water will bind first to hydrophilic regions of the amino acids. At intermediate relative humidities, it will bind to weaker binding sites on the amino acids and also to those previously bound water molecules. At high relative humidities, clusters begin to form. And we can see that they absorb quite a lot of water, about 25% per weight. But this hysteresis, we would normally say in type 4 isotherms, this is quite characteristic of microporous structures, but hair keratin is non-porous. So what is the cause of this? And as I've said, and the title of this project is because it is not well understood. And it's not included in many models for hair water sorption isotherms or other isotherms. And this is what really limits them to being not 100% accurate. There are some very good models out there, some historical models like the Watt and Darcy model, but they don't account for hysteresis. So to make better models for better formulations, we really need to figure out what the causes of hysteresis are. Now, very early on in 1947, suggested that hysteresis was linked to swelling, with some relation to glass transition. So now I'm going to go through a brief sort of hypothesis on what has been accepted as the causes of hysteresis. However, these have not been experimentally proven. So as water is absorbed into hair, the swelling breaks the hydrogen bonding between the hair and keratin filaments and allows hydrogen bonds to form with water. Free energy is lost from the water vapour and is transferred to the hair, allowing some conformational changes, while some energy is lost. These conformational changes lead to a glassy to rubbery transition. And when the water is desorbing, once we go through our rubbery to glassy transition, there is not enough energy for water desorption due to that energy loss in the previous steps. And so that is what leads to a hysteresis. Now, this has been shown computationally in cellulose water systems, this thermodynamic model for hysteresis. So that has been proven, but as I previously mentioned, there hasn't been any experimental models for hysteresis to prove this so far. So hysteresis has also been long shown to be linked to the glass transition of a polymer, in particular with a glass transition being linked to the presence of no hysteresis. Do we have a glass transition in hair? We've got hysteresis present throughout the whole water sorption isotherm. And so we cannot say that we have a sharp glass transition. And if we think back to hair structure, it's far too complex to have a single sharp glass transition point. Instead, we could say, as we see in other proteins, that there is a diffuse onset of glass transition events. And this is more likely with water plasticizing some of the amorphous regions in hair, allowing some glass transition events to occur, but not a full and sharp point. So how do we link swelling to the glass transition? Well, we know that swelling of a fibre allows further accessibility of water to act as a plasticizer. And plasticizers reduce the glass transition point of polymers, so the swelling for hair and its glass transition must be linked. Now, swelling in hair is governed by disulfide bonds. Disulfide bonds are found throughout the hair fibre, and they are what causes its resilience and its strength. So if we want to affect the swelling properties of hair, we need to reduce those disulfide bonds. And that is what I've done in this project. So first, we reduced some disulfide bonds through damage. We then characterised our samples, measured the water sorption properties, and examined the effect on hysteresis. So I'm going to talk a little bit now about the methods we used to reduce those disulfide bonds. So the first method was using thiglycolic acid. This reducing agent is found in a lot of permanent waving solutions and relaxing treatments. And this reduces those disulfide bonds quite effectively. We performed this from 5 minutes to 20 hours so that we could get a range of hair samples with different crosslink densities. However, once disulfide bonds are reduced, they are known to reform over time. So our next step in this synthesis was to methylate these samples with methyl iodide, which is quite a bit of a nasty synthetic step, but it does the job. And so now we have our nicely methylated hair, which has been reduced to different degrees. We also dyed hair, because dyeing hair involves hydrogen peroxide, and this oxidizes disulfide bonds. So we're still getting disulfide bond breakage, but we wanted to examine a different type of damage. All the other additives from the hair dye solutions and formulations will also interrupt some electrostatic bonding within the fibre, leading to more disorder in the hair. And so we wanted to examine how that would affect our water sorption properties. And we chose this red dye, this AHT HDAP dye, as it's quite a simple dimer which forms in the hair. It's a oxidative reaction in the hair, and it's not a reactive dye, so it doesn't interact too strongly with the hair fibre, which is what we were looking for. So now that we had made these hair samples, it was time to characterise them, and we did this using solid state NMR. And here is a spectra, a carbon-13 spectra for untreated hair. And this might be quite a broad peaks in comparison to what many of you might be familiar with solution state NMR. And that's because in the solid state, we don't have that averaging motion from the molecules that you would find in liquid solutions. And this leads to quite significant line broadening. To counteract this, we spin our samples at very high frequencies to try and reduce those line broadening effects as much as possible. And that's called magic angle spinning, and that's what we did here. The cross-polarization aspect is simply using the natural abundance of the protons in our sample to increase the intensity of these carbon peaks, which have a low natural abundance. And so we get our carbon-13 spectra. We have our aliphatic carbon peaks from the amino acids. There's a couple of peaks here in that sort of broad area at around 20 to 30 ppm. We then have our alpha carbon peaks from the amino acids, forming this rather broad peak at around 60 ppm. We then have aromatic peaks from the aromatic amino acids, such as phenylalanine or tyrosine. And then finally, we have a peak which is representative of all the carbonyl groups in the keratin structure. So clearly this is quite a lot of information, and we performed this experiment for all of our hair samples so that we could examine what changes had been incurred due to damage. And here are the spectra. We've got our dyed hair sample on top, untreated hair here in blue, and then our reduced hair samples, increasing in reduction and methylation going down. We reduced hair to 5, 10, 15, and for 20 hours. Sorry, 5, 10, 15 minutes, and then 20 hours. Yes, so I've highlighted some peaks here of interest. The first being this site, which has been starred. Now, this site is where we would expect to see a change in the peak due to the methylation of our disulfide bonds once we had reduced them. However, if you can see, it's not very clear the differences. There's a slight increase, but there's not any significant changes that we might expect. And that's likely due to the fact that we did not use any carbon-13 methyl iodide. We didn't use any labelled methyl iodide, and that would have really enhanced this peak for us to make some calculations. However, that's okay. We can still get a lot of information from these spectra. This peak here at 52 ppm is the alpha carbon of glutamine. And this is glutamine in its beta sheet form. And we can see really nicely from that untreated sample as the peak increases upon dyeing and also increases on reduction, especially for this 20 hours reduced hair sample. And that's really showing us that we're introducing some disorder through damage. We're increasing the beta sheet content of keratin in our hair samples. And we know that this is likely due to those disulfide bonds breaking. And we can measure that directly. This last peak here at 40 ppm is the peak for the beta carbon of crosslink cysteine, or our disulfide bonds. And a reduction of this peak would indicate a reduction in disulfide bond content. And so to measure a relative disulfide bond content for all our samples, we simply normalized this peak to this peak here at about 24 ppm, which we would not expect to undergo any change during our methylation procedure. It has no affinity to either the alpha or the beta sheet carbon. And so if we plot those relative crosslink contents against the reduction time, we see a really nice relationship that we have successfully reduced the disulfide bonds in hair, and quite fully when it comes to about the 20-hour sample. Another really nice feature of this spectra is that carbonyl peak. So as I said, it is made from all the different carbonyls, orientations and forms in this keratin structure, and we can deconvolute this peak using MeshGenova software to identify those contributions. So the peak labelled A is the ordered keratin made from alpha keratin, and the peak labelled B is the contributions from the disordered keratin, this being beta sheet keratin, but also the coiled coil conformational keratin. And we can make a ratio of these peaks using the full width half max of the peaks. And this gives us a relative alpha keratin content, which this relative alpha keratin content is a good measure of order in the samples. And if we plot that relative order against that crosslink content, we can see a really nice correlation. With increasing disulfide bond content, there is more order in the samples, and with the decreasing disulfide bond content, we get reduced order. However, we do see one particular glaring outlier, and that's the dyed hair. So it has a reasonably high crosslink content, but quite a low relative alpha keratin content. So why is that? I've got here just a little figure to try and explain, and we've got our keratin molecules with the disulfide bonds between them in dashes, and this is in tap water, so we've got some metal ions around there as well. Now, when we break our bonds, this is either through bleaching for the dyed hair or reducing for our reduced hair samples, we're increasing that disorder, and that's what we would expect with the reduction of these bonds. But with the dyed hair sample, we have an extra step. And this is because in dyed hair, it's been very well established in literature, it absorbs far more metal ions from tap water than untreated hair alone. And these metal ions have been shown to interrupt the electrostatic bonding between the keratin elements, and this leads to a reduced tensile strength and a depressed melting point for the alpha keratin as measured by DSC. So that can go some way to explain why we're seeing such reduced order in our dyed sample while it still has a relatively high disulfide bond content. And now that we've had a look at all that NMR analysis, let's go on to the water sorption experiments. So in this work, the DVS advantage was used to measure the water sorption for untreated hair and for dyed hair. And the DVS endeavour was used to measure all the reduced hair samples to help sort of speed up the process a little bit with more high throughput measurements. So for each experiment, about 20 to 30 milligrams of hair was used, as it does absorb quite a lot of water. We took our isotherm from 0 to 90% relative humidity in 10% relative humidity steps. We included a 24-hour drying step to really make sure we'd removed any ambient water. Now, normally DVS experiments use what's called a DMDT mode, where a certain change of mass is detected, and then the relative humidity stage will proceed to the next relative humidity step. However, one cause of hysteresis in water sorption isotherms to hair, which has been proposed by some researchers, is that the hair samples haven't reached full equilibration. So to really make sure that we weren't missing out any kinetic data, we stepped 800-minute steps for each stage. And this led to an 11-day experiment, so quite a long experiment there. But as we can see in red for the change in mass with each humidity step change in blue, they have all reached a really nice equilibrium before moving on. And here are some of our results. So I've just got here for the untreated hair, dyed hair and reduced hair. And we can see quite clearly that the damaged samples have a reduced water uptake. And this isn't normally what's seen for damaged hair samples. And so that's quite interesting. It suggests that actually, while we've been reducing that crosslink content, it's the additional hydrophobicity imparted by the methylation and also by the additives in the hair dye formulations that plays a much stronger role in total water sorption capacity rather than crosslink density. As you would expect, fibres with reduced crosslink density are able to swell better and absorb more water. So that was a really interesting thing that we found here. And we were also quite happy with this data, as typically it's very hard to see significant differences in hair water sorption isotherms. And this is largely due to the hair's resilience. It takes a lot to damage hair. So we can see here with our reduced sample, we've really done some damaging experiments here. And now here's just showing all the reduced samples together. And as you can see, they all look fairly similar. And again, that's quite interesting because we went from a 5-minute reduction all the way to a 20-hour reduction. So there's a great spread of crosslink density here, but they are all relatively similar. And again, that sort of highlights the point that perhaps that introduced hydrophobicity from the methylation procedure is the most important factor here for the water sorption property. So now, finally, let's have a look at hysteresis. And I'm starting with just looking at the hysteresis for the untreated hair and for the dyed hair. And we can see initially and quite clearly that there's reduced hysteresis for the dyed hair sample. And we can also see that the maxima hysteresis, the occurrence of maxima hysteresis, for untreated hair is at about 60% relative humidity. But for the dyed hair sample, it's moved to about 50% relative humidity. If we now look at some of the reduced hair samples, we can see that that has shifted even further to 20% relative humidity for the reduced hair that had been reduced for 5 minutes. And then for the 20-hour reduced hair, we can see that that remains quite shifted over. So how does this link to swelling and to our glass transition? Well, as we described before, the glass transition of a polymer is linked to a reduction in hysteresis. That's been shown many times. So we can consider that the maximum hysteresis, the point of maximum hysteresis, must indicate the onset of glass transition events, where any more glass transition events reduces that magnitude of hysteresis, as we see here. So what this is saying for us is that those reduced crosslinks hair samples are having an earlier onset of glass transition events in comparison to the untreated hair. And if we think about polymers in general, this makes sense. Polymers with lower crosslink densities can be plasticized better at lower relative humidities, and therefore we would expect to see these glass transition events occur much earlier than in comparison to our highly crosslinked samples. But to sort of prove this and to see how our NMR data can help us here, we wanted to see if we could correlate the crosslink density of the samples to that occurrence of maximum hysteresis, or where the onset of glass transition events occurs. And that correlated really nicely. We see this strong correlation showing that for those hair samples with lower crosslink density, we are getting that maximum hysteresis occurrence at much lower relative humidities, indicating an earlier onset of glass transition events. So we also did some analysis on the diffusion coefficients. As with this kinetic data, that's one of the benefits. You can fit this data to a model, and here we just used Crank's model for diffusion as applied to a cylinder, where D is the diffusion coefficient, T is time, and R is our radius for our hair fibre. So we used an approximate radius for all the hair fibres here. So to understand the changes in these diffusion coefficients, first we need to understand what it means in hair. And so these are the diffusion coefficients for untreated hair. Now, diffusion in hair is governed by two stages. First being water diffusing through the CMC to the cortical cells. And this occurs until about 40 to 50% relative humidity, where we see this maxima. After this point, water begins to condense in the cortical cells, which leads to a swelling of the cells, which constricts the CMC, which is around the cells, and then that is followed by a reduction in our diffusion coefficient. So how is this changed for our damaged hair samples? Well, we can see the untreated hair in blue here, dyed hair in orange, and our reduced hair in green. And we can see that there is definitely a difference going on here. We can observe that that point of condensation, that maxima, has sort of shifted along for our reduced hair sample, and the diffusion coefficient has remained high for our dyed hair sample. And we can put this down again to the effect of reducing the crosslink density of these samples. If the CMC is able to swell better, it will have a constriction which is delayed. And so that means that those diffusion coefficients can remain higher for longer. Now, as you can see, the reduced hair sample has overall a lower diffusion coefficient across the whole humidity range in comparison to the untreated hair samples. And again, this is likely due to the methylation of this sample. And if we look at the other reduced samples, we can see they follow quite a similar trend with low values for diffusion coefficients due to that increased hydrophobicity, but this delayed point of condensation leads to their swelling. Now, here is the diffusion coefficients for untreated hair during the desorption isotherm. And this has quite a simple one peak, and that has been related to the diffusion from the cortical cells out of the hair fibre. If we look now at the dyed and reduced samples, we see a more bimodal shape appearing. We can see that it's much faster. And if we think about where these two points, these two stages are occurring from, the stage at about 40% relative humidity, similar to the untreated hair, is coming from the cortical cells, but these peaks that are appearing at higher relative humidities, that can be thought of if you consider the ability of the hair fibre to shrink and the diffusion pathways. If you have, as the hair fibre shrinks during desorption, the diffusion pathway for the water will also shrink. And that means that the diffusion for water can remain high. However, if you have a highly cross-linked sample, it's not going to be able to shrink, and therefore the diffusion pathways will remain longer, leading to slower diffusion. So we believe that this additional peak of fast diffusion occurring at high relative humidities, that is related to the more effective relaxation of our hair fibres as they begin to shrink. And we can see from our other reduced hair samples, they show a very similar behaviour. So we've reached the conclusion of this talk. And to cover what we've gone over, disulfide bonds in hair were reduced to different levels, and we found that their disulfide bond content was related to the amount of order in the hair samples, with low crosslink content hair samples having reduced hysteresis, and the maximum occurrence of hysteresis occurring at lower relative humidities. We did some diffusional analysis to show that fibres were better able to swell with lower crosslink densities, and that fibres with low crosslink densities were able to relax faster. So how is that linked to our original question? Is swelling the cause of hysteresis in hair? Well, reduced crosslink densities allow hair to swell better. And a greater swelling allows an earlier onset of plasticisation events and glass transition events. We've shown with diffusional analysis that hair can swell better at higher relative humidities, and they can relax more efficiently during desorption. And this is what we propose leads to a reduced hysteresis across the isotherm. And so, yes, from this experimental work, we think that swelling and a crosslink density has a very strong link to the hysteresis in hair. But clearly, there's always more to investigate with more experiments and potentially a future model. So thank you very much for attending this talk and for listening. I'd like to take a minute to thank my PhD supervisors, Professor Darryl Williams, Professor Rob Law, and Professor Oscar Says. I'd also like to thank my industry supervisor, Jennifer Marsh from Procter & Gamble, who was really important in this work. And also my master's student who I supervised, who helped me with this work, Kitty Lou. So thank you very much, and I'd be very happy now to take some questions.
Thank you very much, Susanna. And yes, just a reminder to our audience, you can now submit questions in the questions panel, or you can raise your hand and we will enable you to unmute your microphone. So just to get us started, Susie, someone has asked us how much sample was typically used for NMR experiments and DVS experiments?
So for DVS experiments, we used about 20 to 30 milligrams of sample because it absorbs quite a large amount of water, so you don't need that much. For NMR samples, though, because the natural abundance of carbon is so small, you kind of want as much sample as you can pack into the rotor. So we ended up using about 80 milligrams of sample there.
Great, thank you. Another question here we have. They ask, for water isotherms, is there a reason for the dye hair presenting smaller hysteresis compared to the other hair samples?
I'm just going to go back to that slide. That's a really good question. So let's go to that hysteresis. No, that's a very good question. I mean, I think through this talk we've understand why it's changed, but to the degree it has changed, there's still a lot more to explore. Reduced hysteresis, it would indicate that perhaps that additional interruption of electrostatic bonding from the more metal ions that are present in hair, that perhaps they're also allowing that plasticization to be more effective, leading to those reduced hysteresis. But definitely something to have a look at in the future.
Great, thank you. Our next question is, do you think the change in crosslink density or the TG of hair will affect the surface area of hair fibres?
So the surface area of hair is typically very small anyway. It's quite a difficult one to measure. The change in crosslink density would, very good question. The damage that you would incur through reducing those disulfide bonds would also lead to stripping of much of the cuticle. And I think that would definitely have an effect on the surface area of the hair fibres. It may lead to a larger apparent surface area as the hair fibre begins to form pores through the damage or gaps in the cuticle. And that could be reflected in its surface area measurements as an increase.
Okay, thank you. Another question here asks, how can you guarantee untreated hair is truly untreated? Is it never had a shower, never used shampoo, or never been dried? What are the benefits in real life in having virgin hair?
So untreated hair, actually, that's an interesting question. People are actually paid to grow their hair without And when we say untreated, we mean no, you can still use shampoos and conditioners, but no straightening, no hair drying, no dyeing, no perming. And so they're paid to make sure they keep their hair in the best condition possible. To account for any variations, we used hair from a batch source. So it was the same hair type. We used North American Caucasian hair here. It was white hair sample. And this hair came from multiple different sources to help average out any differences between those particular individuals who had donated their hair. And I believe there was a second part to the question, but if you could repeat that, that would be great.
Sure thing. Put it up here. And what are the benefits in real life of having virgin hair?
Your hair will undoubtedly be stronger. Your cuticle, without these damaging treatments, such as from heat damage or chemical damage, your hair will just be stronger and less likely to form split ends or breakages. Overall, it is pretty well recommended, but there are some very good products out there to help recover some of these properties which are measured through damage, such as the melting point of your hair, the tensile breakage. There are some excellent formulations out there with the current science that we know.
Brilliant. Someone asks here, have you evaluated the effects of bleaching?
In a broader sense, in terms of, we can use many techniques. So DVS is one of those where we can measure the water sorption properties, see how they've changed with bleaching. We can record an IR spectra of hair or a Raman spectra to examine the peaks and see what has changed with bleaching. Particularly, bleaching will introduce some cysteic acid groups, which can be measured using FTIR. And that gives a really good indication of the amount of disulfide bond damage that you've incurred through your bleaching. And then, obviously, when you bleach your hair, there is a lightening effect. And there are some measurements, photographic measurements out there to understand the extent of bleaching through the colour lifting of the hair sample as well.
Thank you. Someone asks here, from the DVS results, different reduction time seems to have very similar results. Does it mean retention time is not a big factor in affecting the moisture behavior of hair fibers?
As I said in this slide, I think one of the really big things here was that we introduced some methyl groups, because we had to make sure that those disulfide bonds didn't reform. And so this isn't a perfect experiment. Not many experiments are perfect. And in this case, we can see that the effect of introducing that extreme hydrophobicity is that these samples do sort of, and it appears that the hair samples are very sensitive to any introduced hydrophobicity, with all these reduced samples having very similar uptake. But they do, unfortunately, do show differences in their hysteresis, which allows us to have this nice plot.
Great, thank you. Someone has asked, investigated damaging hair with heat or UV?
Yes, so another project I did during my PhD, we looked at how, this wasn't using DVS, but this was using solid state NMR. We were examining how heat damage and also acid and alkali damage affected the mobility of water in these samples. And quite shockingly, we managed to show that even about 50 degrees, so about the strength of your hairdryer, is still going to damage the hair samples quite significantly. that there's a nice linear relationship between hair damage and water mobility in those samples. So that would be another quite nice thing to look at with using DVS to examine how those water populations are affected through heat damage.
Thank you. A question been asked: have you measured some mechanical performance of differently treated hair, and could this be correlated with moisture data?
We didn't do this. There are many studies out there that have done this, and I think that would be a really interesting next step to try and correlate our data to some mechanical performance of the hair fibres. So yeah, great question.
Maybe there's some members of the audience who'd like to work on that with us. Okay, we'll just wait another moment or two for any more questions to be submitted. Okay, questions come in. Have you looked at pH effect?
Yes, so actually in that study where I looked at temperature, we looked at a whole range of pHs from pH 1 to pH 13. We recorded again, this was some NMR work, and we saw that there's this sort of beautiful Gaussian curve when it comes to damage, with hair being relatively stable between pHs 5 and 9. But yes, we're aiming to have a publication out on that work pretty soon. So yeah, stay tuned.
Great, thank you. Someone asks here, if the methyl group reduction had such a significant effect on the hydrophobicity of the hair, wouldn't you have expected the methyl signal from the NMR analysis to increase significantly?
Well, this is again down to the natural abundance of carbon-13. It is pretty low, even with our using as much sample as possible, even with using cross-polarization methods, it is still pretty low. And so if you think about how many carbons are in hair in total, and then if you think about how many disulfide bonds we're reducing, the actual amount of methyl groups we're adding is not very much. And so if you then consider their natural abundance being so low, it does become more understandable why we wouldn't perhaps be able to see it with NMR, but maybe perhaps a different analytical tool.
Okay, brilliant, thank you. That was our last question, and I think we're coming up to the end of our time, so I believe we will wrap up there for today. So thank you once again so much, Susanna, for being with us today to share your findings.
Thank you very much, and thank you everyone for coming along.
Yeah, I can second that. A massive thank you to our audience, especially for all the engaged members who are asking questions at the end. Really great to hear feedback and appreciation from our audiences. So thank you all again for joining, and if you are interested in looking up any of the future online educational events we have coming up, we have 2 extended online workshops taking place in the next month and a half. So you can see these dates on your screen in front of you. So please, by all means, find out more information about these on our website. Especially, we have an event an online workshop next week being hosted by our very own Professor Darryl Williams, who was one of the supervisors of Susanna in her PhD work. So please do check our website at www.surfacemeasurementsystems.com for more information on our upcoming events. And if you have any questions at all, please don't hesitate to send them to science@surfacemeasurementsystems.com or marketing@surfacemeasurementsystems.com. Thank you again to Dr. Melissa, and I hope you all enjoy the rest of your day. Thank you.